So where does this leave us? Well, this leaves us with 2 points that I'd like you to keep in mind as we go further into quantum mechanics, or at least just a little bit. Number one, the wave function psi, which has a spatial value to it, right? So this is a map of psi through distance, is the mathematical quantity that we can apply equations to. And that is the mathematical description of the quantum object, the particle, which has both particle behavior and wave behavior. And that's kind of what we do our math on. And the wave function itself does not have a physical meaning. However, the square of the wave function does have physical meaning. And that is the probability of finding the particle, the electron, for example, at that location. So we can do some math that gives us a psi, which then we can square and then wind up getting a probability description or a probability density function of where the electron is likely to be. And what that means in this case is that the electron in the lowest energy state or the lowest quantum number state is most likely to be in the middle, but certainly not always. There's a fixed probability of it being away from the middle. Notice that the probability then is 0, that it's at or beyond the boundary, in this case with an infinite potential well. Now for the second quantum state, you can see something a bit different. The two equally most likely locations are, I guess, roughly 1/4 away from each boundary. And then at the actual center, the probability turns out to be 0 that we would find an electron there, and so on. And while the equations operate on this one that we'll introduce in a moment, the actual physically meaningful and physically measurable quantity is the square. All right, so let's talk about somebody you've almost certainly heard of, and that is a guy named Schrödinger, Erwin Schrödinger. And he's an Austrian physicist, and he is the one who really formulated the equations that we're going to start to manipulate. And it's essentially a wave equation that is framed in such a way that it applies to the quantum or quantized nature of these particles. And that led to the Nobel Prize in 1933, among other medals, and he's a very important guy in physics. Now, Schrödinger's equation is this: h bar over 2 times the mass times the second derivative of the wave function with respect to x plus the energy of the particle times the wave function must equal to 0. So this means that the atomic particle's wave function must obey this equation. And that's really the teaching from his analysis. And again, this is in this equation a function of x, although it can be a function of x, y, z, and of course 3 dimensions. And this is the wave function. And remember that this is analogous to the standing wave amplitude that we had of a string that we already wrote in our notes, okay? So I know this is hard to wrap your mind around, but stick with me that this wave function is analogous to this amplitude of this wave. And it's just a mathematical description that we can apply quantum mechanics to. And remember then that you may already know this, but this constant is equal to Planck's constant that we've already introduced divided by 2 pi. All right, so h bar is simply h divided by 2 pi. And energy, E, is simply the energy of that particular particle or that wave function. All right, and by the way, this is one of the most important equations in all of physics. So let's, before we dive in and start with using this with some math, let's remind ourselves of some quantum, I'm sorry, not of some quantum stuff, but of some complex numbers. So let's make some notes here about the wave function. Now the wave function has physical meaning. But in a particular way. And that is, first, it's a complex quantity. Keep in mind that psi is equal to a real part plus an imaginary part, where, of course, I is equal to the square root of -1. I know that some of your heads are exploding now because this is, this is really dangerous math, but don't worry, it's not going to go too bad. And, as I've said, the probability of finding an electron, or any quantum particle that we're applying Schrödinger's equation to, the probability of finding an electron at a given location, for example, x, is given by, so again, this probability of finding it at a position is given by the square. And in particular, we like to draw it, or we can write the square as the square of the magnitude, and we can also say that it's the product, or the dot, I guess the complex dot product of the wave function. And this is the only physical meaning attached to the wave function. We cannot measure the wave function itself, but we can measure its square. All right, and I trust that you can remind yourself of some basic properties of complex numbers. I'll show you some here. I've prepared this slide. Of course, if we have a complex number, a plus ib, then its conjugate is a minus ib. And of course, we have a complex plane with the real going this way and the imaginary going that way. We can find its magnitude as a square root of the sum of the squares. We can also then compute this product, which has the complex conjugate in it, keep that in mind, to find the square of the magnitude. All right, so next we're going to manipulate Schrödinger's equations in some simple cases.